Hello, students. Give me just a minute. I'm getting my stuff together for you guys. Can somebody remind me what was the thing we talked about last at our last recitation? I suppose I could roll the tape back and look at that as well.
I think that like what we were going to focus on next, or like what topic we covered
in chapter 2.
Yeah, we talked about getting familiar with the sexy experiments.
Good. Okay, so that's what I remember also. That's awesome.
My headset's not working.
I can hear you. So I don't want you guys to not worry about the experiments that got us to that place, but we don't have time to run back through all of those. So I'll assume that you watched the videos and looked at the experiments from history that allowed us to figure out that protons and electrons and neutrons all exist and are parts of the atom. All right. So I'm going to share my screen and talk a little bit more about those parts of the atom that we discovered using those incredibly sexy experiments from Thomson and Rutherford and Millikan and a bunch of others. Like neutrons were really hard to discover because they didn't have any charge, and figuring out like where that mass was. It turns out now that we know that protons and neutrons are particles that are at the center of the atom. So we call that center of the atom the nucleus. And then our electrons are outside of the nucleus. And there have been lots of different models that have been used to describe where those electrons exist out of the nucleus. All right. So the oldest model is the Bohr model that you see with just like shells of electrons that start out closer to the nucleus and then get progressively farther away. But there are much more sophisticated models than the Bohr model for thinking about how electrons behave, like where they're at outside of the nucleus of the atom. So for right now, before we start getting into how the electrons are behaving outside of the nucleus of the atom that has the protons and neutrons, I want to talk just a little bit more about how we connect all of these subatomic particles to what we actually like see on the periodic table. All right, so let's take a look at the periodic table for a second. I think I have a version of that up on your course homepage. What? I keep on discovering ways that our course homepage isn't quite as good as it could be. So that's where I would get the periodic table if I was you guys. I would get it from that first module, but I want to look at it on the whole screen. So I'm just going to open my version of it in my documents here. Okay, sweet. So what I want to look at is, we'll go simple first. We'll look at hydrogen, all right? And talk about how many of each kind of those subatomic particles, protons and neutrons and electrons, a given hydrogen atom might have, all right? So when I look at hydrogen's symbol on the periodic table, I see two different numbers, one above and one below, all right? So first of all, the symbol, the short version of the name, that element symbol is something that like we want to be able to recognize those over time. I'm not going to make you memorize the periodic table, but not all of the symbols are just like the first letter or two of the name. Some of them are different. For example, potassium is not PO, that happens to be polonium instead. All right. Potassium is K. A lot of times when the symbol doesn't match up with the first couple letters of the name, it's because the symbol comes from the Latin name for that element instead. So we should recognize those so we can like guide our way through the periodic table a little faster. All right. So sodium is Na from natrium, which is the Latin name for sodium, for example. All right. Copper is Cu instead of Co. One, because Co is cobalt, and two, because Cu comes from the Latin cuprum, which is the Latin name for the element copper. So take a little bit of time to look at the more common elements like tin, copper, iron that have different symbols than just the first couple letters of their names. And it will help you get faster at finding those on the periodic table, because in the end, I don't make you memorize the periodic table. We'll have to use it all the time. So if you know where to find copper on the periodic table, at least generally speaking, you're going to spend a lot less time on exams when you need to find those elements to do problems quickly. All right. But for right now, let's just look at hydrogen's little part of the periodic table. Up here, that top number is what we call hydrogen's atomic number. So that atomic number tells us how many protons every hydrogen ever has. The number of protons that an atom has tells us the identity of the atom. All right. So if an element had a different number of protons than one, it wouldn't be hydrogen anymore. So every hydrogen ever has exactly one proton in it. And when we talk about specific hydrogen atoms, we'll often use this notation where we'll use the element symbol, and then there will be a number up here and down here, and then sometimes a charge up here. All right. So I'm going to just label those as X, Y, Z, and we'll talk about what each of those numbers means. All right. And then we'll give examples because it's pretty easy with more examples. So X is what we refer to as the mass number for that particular hydrogen atom. Y is the atomic number. That same number that we see up there at the top of the element symbol. And then Z is the charge on that particular atom, if the charge isn't zero. If it's zero, we don't see anything there at all. All right. So let's look at a very simple hydrogen atom. And very often this Y is not present at all. And the reason why is because the element symbol tells us what that atomic number is anyway. The fact that this is hydrogen right here tells us that the atomic number has to be 1. Because if it was something other than 1, then the element symbol wouldn't be hydrogen anymore. All right. So I'm going to leave this one out because most of the time chemists don't use it. They use the symbol to know what the atomic number of that element is anyway. So hydrogen has an atomic number of 1. All right. And we can see that by hydrogen's entry on the periodic table. And let's look at this particular version of hydrogen with a mass number of 1. Now, the mass number tells us the total number of protons plus neutrons in that particular atom. Not every hydrogen is identical in terms of its mass number. Now, every hydrogen has the same number of protons, but hydrogens can vary in how many neutrons they have. All right. So elements can vary based on how many neutrons they have. If we have a big pile of hydrogens, an awful lot of them will be hydrogen 1s, and just a small number of them will be hydrogen 2s, and then a really, really, really small number of them will be hydrogen 3s. 3 different versions of hydrogen. All right. So we call these different versions of hydrogen different isotopes. And we'll learn what isotopes mean when we start to think about what that mass number tells us about each one of those hydrogens. All right. So note that this hydrogen doesn't have any charge shown. We know that protons, at least the way that we've defined their charge, have a charge of +1. And I'm going to make this bigger so you guys can see it a little easier. Whoop. All right, that's a lot easier to see. I can even zoom in more. Much better. All right. So protons have a charge of +1, electrons a charge of -1, and neutrons a charge of 0. You guys give me just a second. My wife is calling and she just had a dentist appointment, so I want to make sure that she's not like having a root canal right now or something. Sorry, I'll be right back. Hello, wife. I'm in class right now. What can I help you with? No, it's fine. I called to make sure you're okay. All right. Yeah, so any happens or you so they can fix all of them without I love you. Okay, I love you. I'll see you soon. Bye. Mostly good news. That's great for both TIFF and our wallet also. All right. I care a lot more about the TIFF than the wallet. So protons, a charge of +1, electrons, a charge of -1, and neutrons, a charge of 0. So where does this mass number come from anyway? It comes from the fact that protons and neutrons each have a mass of about 1 atomic mass unit. All right. Now we use the term atomic mass unit because it's a really, really small number of grams. If you want, in your book, you can look up the conversion between what a proton weighs in atomic mass units and what it weighs in grams. All right. That's just another mass unit that's really small because the parts of an atom are really small. The important thing for us to know is that protons and neutrons each have about 1 atomic mass unit worth of weight. Compared to that, electrons have about 1/1000th of an atomic mass unit in weight. So if we're thinking about where the mass in the atom comes from, almost all of it is the protons and neutrons, and very little of it is the electrons. So the reason why we call this the mass number, the total number of protons plus neutrons, is because that's where most of the mass in the atom comes from. And if each of those has a mass of about an atomic mass unit, then adding up our number of protons and neutrons gives us the approximate mass of that atom. All right, the approximate number of AMUs that it is. So if this hydrogen has 1 for its mass number, and we know that hydrogen being atomic number 1 has exactly 1 proton in it, how many neutrons does that hydrogen have to have? Rudy says 0. Rudy is correct. 0 neutrons. So our mass number is our number of protons plus neutrons. Well, if we've got 1 proton, there's no mass left for any neutrons. It turns out that that is the most common version of hydrogen. Hydrogen with 1 proton and no neutrons. All right. And if we look at a big pile of hydrogen atoms, like 99.97% of those will be hydrogen ones, hydrogens with 1 proton and no neutrons. A small percentage of them, all right, about 0.0028% are hydrogen 2s. Now, we haven't talked about electrons yet. The fact that there isn't any charge on this hydrogen tells us that there have to be just as many positively charged things as there are negatively charged things in that hydrogen, which means we also have to have 1 electron in this hydrogen, right? So a positive, so 1 positive charge and 1 negative charge cancel out and give us 0 net charge on that hydrogen. For hydrogen 2, we have a little bit more mass left over after we take out that proton, right? So hydrogen 2 would have 1 proton, 1 neutron, and 1 electron. Now, I didn't even list it, but there's a small trace amount of hydrogen that even has 1 more neutron than that, hydrogen 3. It's commonly referred to as tritium. All right. So that version of hydrogen, that isotope of hydrogen, has 1 proton, 2 neutrons, and 1 electron. So I'm going to go grab a sample of tritium that I happen to have sitting around in my house. It might not be exactly what you expect, but it's pretty cool anyway. So I'm going to be right back in a second. Now, it's not dark enough for me to turn out all the lights in this room because I don't have curtains over everything. We just moved into this house a couple months ago and are still remodeling. But if you take a look right here, you will see my Luminox watch. I broke the strap on it and I'm still trying to decide whether I want to order one of the factory ones or like order something aftermarket to make it a little fancier. All right. This is a nice waterproof watch that is a lot of special forces use this. And the reason why is because if I turned all the lights out in this room and it was completely black, I would still be able to read this watch just fine. If I zoom in and look even closer at the watch, you'll be able to see why. So I'm going to point at it. You can see small little tubes there and there and there, and then tubes on the hour and minute hands as well. Those tubes are actually tubes that are filled with tritium, all right? Not tritium, just hydrogen, the element itself, but I think it's actually water that contains mostly tritium instead of regular old hydrogen. So instead of H2O with just regular hydrogen, the hydrogens are mostly tritium instead, that special kind of hydrogen with 2 neutrons. Now, why is it that tritium glows? It turns out that tritium is a radioactive isotope of hydrogen. So as it very slowly decomposes, it releases light, and you can see that light, all right? I think that the half-life of tritium is something like somewhere between 5 and 10 years. So in another 5 or 10 years, these tubes will only glow half as brightly as they did. In another 20 years, the tubes will only glow a quarter as brightly as they did. So that's a place that isotope of hydrogen is like useful in real life. We use it because it glows, so we can use it for like glow in the dark stuff that doesn't need to be charged up. So it's not like a chemical reaction that we excite a sample and it glows for a while through phosphorescence. This glows because it's radioactive. All right. Now, older watches used to use radium paint instead because it was radioactive and made the dials glow in the dark. That radioactivity is a lot more dangerous than tritium. So if you ever watch or read the novel Radium Girls, I think is the name of the novel, it talks about the toxic effects from women that were employed in the industry where they were painting the dials on watches and clocks with radium paint, and they would like lick the paint brushes to make a nice fine point, and they were poisoning themselves with toxic radioactive radium over time, so not so great. Tritium is a lot less dangerous. I don't mind having this radioactive sample in my house. So any questions about how we can figure out how many of each of these kinds of particles we have based on that mass number? Because the atoms get a lot bigger than hydrogen, all right? Now, also, we sometimes have atoms that have a charge. So for example, hydrogen can sometimes have a +1 charge, and it can sometimes have a -1 charge. Now note that +1 or -1 are just listed as plus or minus, all right? If the charge was +2, it would be listed as 2+, all right? It's just the way that chemists list their charges. Don't shoot me, I'm just the messenger, all right? Somebody decided that was a good idea a long time before I was born. So if this hydrogen has a +1 charge, how many of each kind of particle would it have? How many protons and neutrons and electrons? Well, still the same mass number, so we know that hydrogen still has 1 proton and 0 neutrons. But that plus charge tells us that it has more protons than it does electrons, all right? So if it's a +1, it has to have 1 more electron than, or sorry, 1 more proton than it does electrons, which means that that hydrogen has 0 electrons. Now, what about this hydrogen with a -1 charge? The mass number still tells us 1 proton and 0 neutrons. The charge tells us that this hydrogen has 1 more electron than it does protons. That's how we would end up with a -1 charge, right? 1 more negatively charged thing than our number of positively charged things. So this hydrogen with a -1 charge has 2 electrons compared to only 1 proton. Does that make sense to everybody so far? Hello, darkness, my old friend. I love when I ask a question and then just like, Mia, question.
Hey, yeah, okay, I'm not sure if I missed it, but why do they vary sometimes? Like why would
Like, why is the universe the way it is? I don't
that's
know.
fair. Okay.
Yeah, that
Right.
legitimate, like it's just a fact, right? So in a pile of hydrogen atoms, most of the hydrogen atoms will have no neutrons, and 0.00027% of them will have 1 neutron, and then a really, really small number will actually have 2 neutrons. It's just the
Okay.
way that atoms work, all right? So lots and lots of atoms have multiple isotopes, different versions of the atom. And remember that isotopes only vary in how many neutrons they have. That's important, okay?
Okay.
So let's look at some other examples that are well-known examples of how many or different isotopes of atoms. And the other thing that I haven't touched on yet, we'll get to more examples, but let's stick with hydrogen for one more thing, all right? If we go back and look at hydrogen's symbol on the periodic table, there's one more number that we haven't talked about yet. That number at the bottom is what we refer to as hydrogen's average atomic mass. So we get that number by actually calculating what the average mass of a hydrogen atom in the pile is. And I've given you a little bit more information here. So remember we said that hydrogen 2 has a mass of about 2 atomic mass units. Well, here are the real masses of each one of those isotopes. That's really close to 1, right? So that's hydrogen 1's mass. This is really close to 2. That's hydrogen 2's mass. We're not even going to worry about hydrogen 3 or 4 or 5 or 6 or 7, which all those isotopes exist, but none of them, there's hardly any of them. All right, not enough to influence that average mass at all. So how did we calculate that the average hydrogen atom has a mass of 1.01 atomic mass units? Well, what we did was we calculated a weighted average of the mass based on how much of each of those isotopes there were. All right. So Let's actually do that calculation together and see that we come up with the same thing that our periodic table has for the mass of hydrogen. Now, to fit everything on the screen, I'm gonna have to zoom out a little bit. Wow, I've used lots of space already. That's good and bad, I guess. I might be able to fit the calculation up here at the top. So let's try it. So if I'm calculating a weighted average, I have to weight it based on the percentage of each isotope that I have. All right. So if X is my average atomic mass for hydrogen, and I get that by looking at all 100% of my hydrogen atoms, then I'm going to calculate that weighted or that average atomic mass, knowing that 99.972% of my atoms have a mass of 1.007825 atomic mass units. And then I'm going to add to that the 0.00028% that have a mass of 2.014102 atomic mass units. You could also set this calculation up with fractions instead. So the whole pile of hydrogen atoms, so just one instead of 100%, have this average atomic mass. And instead of percentages, we would use the fraction of each one of these. So the fraction corresponding to this would be 0.99972 times 1.007. All right. So I'm just setting this up as percentages because it's a little easier to understand. All right. All my percentages here have to add up to 100%. So that's what I mean by a weighted average, right? Weighted based on what percentage of each of those isotopes we have. So if I do this calculation and solve for X, X should tell me what the average atomic mass of hydrogen is. So I'm going to do this on my calculator really quickly. All right. 99.9. Oh, I'm going to turn my calculator on. So 99.972 times 1.007825 plus 0.000. Oh wait, that I don't think that I've done this correctly in terms of it should be 0.0. It should be 0.028%. That's how I get these to add up to 100%. So 0.028%. And these numbers are just numbers that I looked up for what percentage of each of those isotopes we had. 0.028% times 2.0142. Okay, I'm going to turn this off of scientific mode. And then I have to divide by 100. So there is what I'm calculating based on those isotope masses as my average atomic mass of any one hydrogen in the pile. Does that jive with what we see on the periodic table? So to three significant figures, are they the same exact thing? 1.008, doesn't that round up to 1.01 at three significant figures? Sure it does, right? So that is how we would calculate the average atomic mass if we knew what the isotope masses were and what percentage of each of them we had. All right, let's do another example of that together, and we'll look at an atom that's pretty easy to do this with because it only has two isotopes. All right. Actually, let's do one that's a little harder because it's the only other one that I have the percentages for. So silicon right here has 3 different isotopes. All right. And you can see each of their atomic masses and then what percentage each one of them is in terms of how common it is. So we could set up a calculation to figure out what the average atomic mass of a silicon atom was. Now we would look to see if we were right by looking on the periodic table. So if we do this calculation correctly, our average atomic mass of silicon right here, element number 14, should be 28.09. All right. So let's do our calculation together. And I'm going to try to sort of fold my paper so that I can keep the information all in one place. We're pulling out all the stops here. All right. So I folded my paper up so that I could do the calculation right next to my information here. So if I'm calculating the average atomic mass of all 100% of my silicon atoms, 92.23% of them are going to have a mass of 27.976927 atomic mass units. And then 4.67% of them are going to have a mass of 28.976495 atomic mass units. So note that that is the real mass of silicon 29. Remember, 29 is about what that isotope weighs, right? So is that pretty close to 29? Heck yeah, it's pretty close to 29, right? So we said that protons are about 1 atomic mass unit. Neutrons are about 1 atomic mass unit. So yeah, this isotope math is pretty close to what that isotope number tells us. All right. And then finally, the third one of these, 3.10% of our silicons will have a mass of 29.973770 atomic mass units. All right. So from here, all I have to do is solve for X, right? That is the weighted average that we get by weighting in what percentage each one of those individual isotope masses give us. So let's do it together. All right, my 92.23% of these have a mass of 27.976927. All right. And then we add to that the 4.67% that have a mass of 28.976495 atomic mass units. And then we add to that the other 3.10% that have a mass of 29.973770 atomic mass units. So, and when I hit enter here, I will have done the entire right-hand side of the calculation. And I'm going to have to divide this number by 100. So divide that by that 100% on the other side to get my average atomic mass of a silicon. All right, 28.085. So how does that compare? 28.085. How does that compare to the average atomic mass of silicon on the periodic table? If I round it to 4 significant figures, do I get the exact same mass as what we see on the periodic table? I do, right? Yeah, that's awesome. So that is where those average atomic masses come from. All right. Now I would expect you to be able to calculate an average atomic mass if I give you the percentages and the isotope masses. All right. So you've seen how to do that weighted average calculation. You should be able to do that for yourself. All right. Now I want to give you a problem that's a little bit harder that has to do with these average atomic masses. All right. So let's see if you can figure this one out. It's a bit of a brain teaser. So here are the two isotopes of bromine and their isotope masses. If we look at bromine on the periodic table, there is its average atomic mass to 4 significant figures. So what I want you to tell me is what percentage of each one of those bromine mass or isotopes are there in our pile of bromine atoms. All right. So what percentage of our bromines are bromine 79s and what percentage of our bromines are bromine 81s? See if you can do that by using that formula that's very like the weighted average formula. See if you can use that formula to calculate what percentage of each one of our bromine isotopes we would have. So I'm going to try and perform some more magic here for just a second. Doing paper folding tricks to give myself more space to work with here. And I'm going to do some window moving tricks also, so we can give ourselves a little bit bigger picture to look at while we still can see bromine on the periodic table. All right. So let's think this through a little bit. 100% of our bromine atoms have what average atomic mass? The periodic table says the average atomic mass is 79.90 atomic mass units, right? So we're trying to figure out what percentage each one of those isotopes is. So on the other side, one of these isotopes has X percentage of the total. And that isotope has a mass of 78.918337 atomic mass units. And the other one of our isotopes has some percentage, so I'm going to call that Y percent. And that other isotope has a mass of 80.916291 atomic mass units. So this seems like it might be an impossible problem to solve, all right? This is the classic idea of we have only one equation, but there are two unknowns in that equation. Is there any way that we can simplify this to make just one unknown? Is there anything more that we know about these two percentages? What do we know about these two percentages? Because those are the only two isotopes of bromine, at least the only ones we have to worry about.
They
What do
equal
those-
100%.
They have to equal 100%, right? Awesome. So can't we write one of these like in terms of the other one? So instead of Y, we could say 100 minus X right here. Whatever X was, Y would have to be 100 minus X, right? Does that make sense to everybody?
Yeah.
Okay, so I'm going to reset this up, but use that information that those two isotopes have to be a total of 100%. And I'm not going to write all 6 decimal places because we're rounding to 4 significant figures at the end anyway. All right. Since our average atomic mass is only 4 sig figs, then we can't know our percentage is more than 4 sig figs anyway. So our other isotope, 100% minus X, would have an isotope mass of 80.916 AMUs. Okay, so now let's try and solve this algebraically. This is a little tougher to solve, so we'll want to actually do some simplification. We're going to have to multiply each of these terms out. So 79.9 times 100, 7,990 AMUs on this side. And then on the other side, I'm just going to cut the variables out because we know that those x's, the x is a percentage anyway. So 78.918 times x. And then here's where you might run into issues. Remember that we have to multiply both of these two terms by 80.916. All right, so plus 8091.6, and then minus 80.916 times x. All right, that's what I get when I multiply out these terms algebraically. And then I'm going to group my like terms. So I'm going to do that by moving both of the x terms over to the left, which will make a positive x term for me. All right. So, and I'm going to move this term over to the right. So 8091, whoops, 8091 minus 7990 is 101. So I'm going to keep that on the right side. And then 80.916 minus 78.918 is 1.998. Wait a second, I haven't done that correctly. 78. I did do that correctly. I must have made some sort of mistake in my calculation here. This is what I get for working for too many hours on committee meetings before I teach my one big class for the day. My brain has exploded before I even get here. Just error checking myself here. 91.6, that looks right. So it looks like this step that I did, everything is correct in it. All right. No, it does. That's perfectly fine. All right. So 1.998 is equal, or sorry, 1.998x is equal to 101. All right. So I've simplified from here to here, and then I divide both sides by 1.998. And I'm getting x is equal to 50.55%. So it looks like my bromine 79 is 50.55% of my bromine atoms. And because we know that the two percentages have to add up to 100%, that means that I can do 100 minus that. And then to four significant figures, my bromine 81s have to be 49.45% of my pile. So does that answer make sense with what we see as the average atomic mass of bromine? If each of those isotopes accounted for about 50% of the pile, wouldn't our average atomic mass be somewhere close to right in the middle between 79 and 81? It would, right? And is our average atomic mass pretty close to right in the middle between 79 and 81? It is. So we did our math correctly there, all right? And it turns out that that's real data for bromine, all right? So in a big pile of bromine atoms, about half of them are bromine 79s, and about half of them are bromine 81s. We actually see this in the world of organic chemistry with an instrument called a mass spectrometer that actually measures the masses of whatever molecules we put into it. So if we have a molecule that has bromine in it, we always see two different peaks for the masses of that molecule. And the two peaks are almost the same size as one another because we have just as many of the bromines that are smaller as the bromines that are bigger in mass, all right? So it turns out that actually this peak would be slightly larger because a slightly larger percentage of our bromines are bromine 79s. But wherever we put bromine into a molecule, the result is we end up with a pile of molecules that have two different masses, all right? Because half of our bromines have two less neutrons than the other half of our bromines. So that's really neat. Whenever we measure the masses of molecules that have bromines, we always see both of those isotopes in the masses of the molecules that have those bromines in them. Wow, the chat went wild. May I screen? Mia, you don't need to ask permission. So we're recording all these meetings anyway. You can always screenshot whatever you want to. All right. That's like a lot less invasive than recording the whole meeting. So all these meetings are available on YouTube. They're not listed, but anybody can access them. So I don't advertise them or anyway. I don't try and monetize my YouTube channel. It's just there as a resource for my students. And chances are nobody except for my students is ever going to see my YouTube channel because it's not listed anyplace. And I can tell you for certain, I'll never be good enough at Rocket League to put highlights from Rocket League on my YouTube channel. All right. I get smoked at Rocket League all the time. So I'm a low platinum player in 2s and still a gold player in 1s. I'm not very good. All right. So if you want to screenshot that problem, there's your screenshot right there. All right, before we move on and start talking about more sophisticated models of the atom, I want to do one more example of an isotope so that we make sure that we understand that notation for isotopes. So let's take a look at this particular atom of gold. All right. I can make this a little smaller so we can see everything. All right, so its mass number is 201. Its charge is +2. And right here is where you see gold on the periodic table. All right, group 1B. So what I want to know is how many protons, how many neutrons, how many electrons are there in that gold ion? So how can we find the number of protons? Somebody tell me how, not just what the number is, but where do we find that? In the chat. Rudy says periodic table. Okay, so what about the periodic table tells us that gold has 79 protons? It's got to be that number right above gold, right?
The atomic number.
Yeah, the atomic number tells us that every gold atom ever in the history of gold has 79 protons. So the original chemists, the oldest school chemists that existed, were during the Middle Ages. Chemists tried to turn everything into gold because it was a precious metal. We called that alchemy. All right. They weren't very successful in doing that because it's very, very difficult to transmute elements. All right. It's very difficult to take some other metal and turn it into gold. And the reason why is because generally speaking, atoms don't gain or lose protons. All right. When we talk about most chemical reactions, we're talking about atoms gaining or losing electrons in chemical reactions. So it doesn't change gold into something else. So gold can give away some electrons or in rare cases pick them up. But generally speaking, atoms react by giving away or picking up or sometimes sharing electrons. That's how most atoms behave. Since our mass number is 201, I can subtract 79 from 201, which I should be able to do in my head. But again, meetings have destroyed my brain capacity. All right. So 122 neutrons. And then what about my number of electrons? Where would I figure that out from? So we know that the charge of this particular gold atom is a +2. What does that tell us about its relative number of protons and electrons?
It's 2 less than the number of protons.
Right. We have to have 2 less negatively charged things than our number of positively charged things. So we have to have 77 electrons here. That's how we would end up with a net charge of +2. Very good. All right. So you'll be asked about something like that on the exam. I promise you. All right. It's on the practice exam 1, which you can already see if you scroll down on the course homepage. The exam's not for a little while yet, but you can start looking at practice exam questions, because what better way to get ready for one of my exams than to look at the old version of the same exam? That's literally a version of this exam that I have given to a previous class, right? Why wouldn't you want to look and see what kinds of things I think are important as you go through the first few chapters? Rudy, was that okay, a Rocket League joke? Because that's one of the chat things that you can see in Rocket League is just okay with a period. No, okay. Okay. So anyway, that's when you want to like express the fact that something happened and you don't think that it was very good. Like if somebody makes a great shot on you and you want to crap on their shot, you say, okay, like whatever. Yeah. Anyway, I don't say things like that because I'm never good enough to be cocky in Rocket League. I just get smoked all the time. Okay. Mia, question.
Yes. Okay. So I'm sorry. May you please explain why there were 77 electrons again?
Yep. So that +2 charge tells us that there are 2 more positive charges than there are negative charges in that particular gold thing. So since there are 79 positive charges, 79 protons, there have to be 2 less negatively charged things, electrons.
Okay, cool.
How far were we supposed to get today? Ooh, we're supposed to get to the mole and molar mass today. That's probably going to take us a little longer than just today. No big deal. If you look, we've got an entire period for review and catch up. So if I'm a little bit behind at this point, like I've planned that contingency into the schedule, which is great. So there is a video from chapter 2 that talks about how the periodic table is organized. All right. Let's review some main points of that. All right. And then after that, we'll be done for the day. We'll save the mole and molar mass for next Monday together. Okay. Because that's like a little bit too big of a bite to chew on after we've already done this with the different subatomic particles. All right. But let's look at the periodic table for a second and take a quick tour of that, and then we'll be done for the day. Okay, So the first part of the periodic table that I want to point out to you that's really important is this little stair-steppy line, okay? So that stair-steppy line on the periodic table is essential because it separates the periodic table into a left-hand side and a right-hand side. All the elements to the left-hand side of the periodic table are the metals, all right? Now, why is that important? Because metals behave differently than non-metals do, all right? We're gonna learn more about how those things behave, I think like at the end of chapter 3, all right? But we have to know what the difference between where the metals are and the non-metals on the periodic table because they behave very differently from one another. So all of the elements to the right-hand side of that stair-steppy line are the non-metals. Now, your book, if you read closely, will say that some of the elements like silicon and germanium and arsenic, antimony, ones that are really close to this line are kind of somewhere in between metals and non-metals. They're called metalloids. We don't have to really worry that much about the metalloids. For us right now, like to a first approximation, if it's on the left-hand side of that stair-steppy, we'll call it a metal for now, all right? If it's on the right-hand side, a non-metal. So it turns out that the closer we get to that line, the less metally our metals are, and the closer we get to that line on the other side, the less non-metallic our non-metals are. But for right now, that'll be our like line of demarcation between the metals and the non-metals, all right? So then I want you to look at this very first column on the periodic table. Now, the columns on the periodic table are super important because columns actually contain elements that all tend to react in very similar ways. So elements that are in the same vertical column on the periodic table, they behave similarly to one another, all right? Now, almost all of these elements here are elements that we refer to as the alkali metals. That's the group 1A elements on the periodic table, all right? The only one of those that isn't a metal is actually an exception to the little stair step thing. Anybody know which one of these is a non-metal, even though it's all the way over here on the left of the periodic table? If you don't, it's all right. Turns out hydrogen is an exception to the little stair-steppy line thing. So hydrogen is a non-metal, even though it's in group 1, all right? But the rest of these, from lithium on down, we refer to those as the alkali metals, all right? The group 1 metals are the alkali metals. So metals, generally speaking, tend to be shiny. They tend to be solids at room temperature. As a matter of fact, every metal that we know of on the periodic table that exists for more than a microsecond is a solid, with only one exception. You probably know that exception or can think of it if you think hard enough. Anybody know a metal that's liquid at room temperature?
Mercury?
Mercury. Yep.
Yay!
So mercury is right down here, Hg. It's another one of those that its symbol is not the first 2 letters of its name because its symbol comes from its Latin name, all right? But mercury is a liquid at room temperature. There's actually one other metal on the periodic table that's not a liquid at room temperature, but if it was a super duper hot day, it might melt, all right? And that is germanium. Oh, sorry, not germanium, gallium, all right? So gallium right underneath aluminum is a metal, but it melts at a pretty low temperature, all right? So if you look, let's see where I can find that. So I'm Google searching gallium spoon, and it is a great prank spoon. So you can buy this spoon. It's a really expensive prank because gallium's not very cheap anymore. All right. $8.99. Wow, $8. That's not too bad. All right. So the disappearing spoon is a spoon that is made of gallium. The reason why it's awesome is if you give this spoon to somebody to stir their coffee with, hot coffee is hot enough to melt gallium. So it liquefies and ends up in the bottom of the cup when you go to stir your spoon. So you pull the spoon out and it is melted away. All right. So that's one that's like, it's pretty close to a liquid at room temperature, but not quite. It's a really cool prank. All right. Then you have to worry about getting your molten gallium solidified and out of the bottom of the cup. And actually, like if you had a mold, you could just melt the gallium. It doesn't take very much to melt it, and then pour it back into that mold and remold your spoon and then trick somebody else. All right. So that's pretty cool. So let's get back to the other groups, the other vertical columns. So when I say a group of elements, I'm talking about elements that are in the same vertical column. So the group 2 elements, we refer to those as the alkaline earth metals. All right. So alkali and alkaline talk about what happens when we dissolve those into water. When they react with water, it ends up making the water more alkaline in pH. It makes it a basic solution. All right. We don't have to know why that is yet. That's later in the year, but that's why these have those names. All right. Because when we react them with water, the solution ends up being a basic solution. So we're going to skip all of these elements in the middle here. All right. And move over to groups 3A through 8A. So if I say group 3 without any other like clarification, I'm talking about group 3A. All right. So groups 1 through 8 are these 2 groups and then these other 6 groups. We refer to those 8 groups as the main group elements. All right. Those are the main group elements. And by the main group, it means like we leave out all these ones in the middle and then all these down at the bottom also. So when we get to group 7A, those have a nickname, and it's a nickname that you've heard before in other contexts. We call these the halogens. All right. So if you've ever heard of halogen light bulbs, they contain samples normally of, I think, iodine. And when that iodine is heated and an electric current is passed through it, it glows. All right. So that's where you get the light from in halogen light bulbs, is chlorine or bromine or iodine, probably bromine or iodine, more likely than chlorine, because chlorine's pretty toxic as a gas. All right. And then finally, group 8 of the main group elements. So a long time ago, we used to refer to these as the inert gases. Inert is a fancy way of saying they don't react with anything. All right. They don't do chemical reactions. Now, somebody came along about 60 years ago and ruined that for us because they were able to get krypton and xenon both to react with fluorine. So we know now that krypton and xenon will do some chemical reactions. All right. So we can't call these the inert gases anymore. We call them the noble gases now, the noble gases. All right. So now you know the nicknames for 4 different groups on the periodic table. Group 1 are the alkali metals. Group 2 are the alkaline earth metals. Group 7 are the halogens. And group 8 are the noble gases. All right. For any of the ones that don't have a group nickname or that you don't know the group nickname, you can just use the top element in the group as the name or talk about just its group number. So we can say group 6, or we could say the oxygen group. All right. Either one of those is perfectly fine to describe this. This one actually does have a nickname. They're called the chalcogens, but nobody remembers that, so don't worry about it. All right. So what about all those elements that we missed right in the middle here? So these elements in the middle are a transition between the first 2 groups of the main group elements and then the rest of the main group elements. So, and they're all to the left of our stair step. So we know that all of these elements in the middle are metals, right? They're all left of the stair step. So all those in the middle are metals. So these are what we call the transition metals. Those elements that are in those 10 groups in the middle of the periodic table are the transition metals. And then finally, these elements down here at the bottom of the periodic table are sort of in a weird place. All right. This is like a call out box because all 14 of this row here are in between lanthanum and hafnium. If you look at the numbers, Here's atomic number 57, and then we skip all the way to 72 with hafnium. Well, how do we get from 57 to 72? There's 58 through 71 down there, all right? So we call these two rows, all right, not groups, these are horizontal rows. We call those the rare earth elements because most of them are pretty uncommon on Earth. Now, one place that it's important for us to think about rare earth elements is with the current design of the batteries that we use for electric cars. So high capacity batteries right now use some rare earth metals in their construction. The problem with that is we don't have very much of any of those rare earth metals on Earth. We're mining them at a higher pace than we ever have been before because we need them for those batteries. We better be recycling them from those batteries because we're going to run out of those rare earth elements. All right. So if you want to be extremely, like obscenely rich, here's my suggestion to you. Come up with a design for a high capacity battery, like for a car or something, that doesn't use any rare earth metals in it. If you can do that, you will avert a very important problem that faces mankind right now, which is our current design for those batteries uses elements that we don't have very much of, all right? Also, you will make those batteries considerably cheaper to make by not using those elements anymore, all right? So you're doing the Earth a favor and you're doing your pocketbook an enormous favor if you can redesign those batteries to take out those rare earth elements. So that's pretty much our tour of the periodic table. All right, I think that there is a version of that in the chapter 2 videos. Has anybody watched all the chapter 2 videos already? If you have, did you see the tour of the periodic table in there someplace? I think it's in there. I don't remember anymore. It's been a long time since I recorded those videos for the first time. But if not, now you've taken your tour of the periodic table with me. All right, I think that's it for tonight. All right, when we come back next time, we are going to talk about the mole and molar mass. All right, so that is our beginning of our discussion of how we handle what we call stoichiometry in chemistry. And the mole is basically just like a group of something that's really big, and the group size fits things that are really small, like atoms or molecules. So we'll talk more about the mole and how we can use it to our advantage next time that we're together next Monday. All right, I'll be posting our chapter 2 homework really soon, and that chapter 2 homework is not going to be due until next Friday anyway. So for right now, be working on your chapter 1 homework that's due in a couple of days. All right, make sure that you're signed up for Chem 101 homework, that you've enrolled in our section, and that you're working on that because you got only a couple of days left to do it. If you haven't enrolled yet, I'm gonna change how that looks on our course homepage so it's easier for you to see where to sign up for that, because apparently some people didn't know how to do that. I got a student in office hours today. It's like 101 homework. Where is that? What does that mean? Okay, well, if you haven't signed up yet, then it's time to sign up. Do you need to upload the lab stuff before Friday? Yes, and I will make a video to show you how to do that. All right, so just make sure that you have your lab done, and it'll only take you a second to actually upload it. So just make sure that you actually have the lab experiment finished, and I'll give you guys instructions for how to submit it. It's going to be really easy. All right.
Okay.
And that's true for no matter whether you did the virtual version of the lab or whether you did the in-person version. All right. The virtual version, you're going to make PDFs of what you've done with the worksheets and turn those in. Or if you did the in-person version, you're going to take pictures of each of your worksheet pages and turn that in as a PDF. It's very similar.
So that's due tomorrow then?
Friday.
Friday, okay. Okay.
Friday by midnight. Yep. Okay, if there aren't any more questions, then I guess I will see you guys next Monday. Remember, I still do have office hours tomorrow from 4 to 5. So if you're uncomfortable with something from homework or need more practice, make sure that you come by. And some of you I will see in person on Friday morning for lab, and I look forward to that. All right. So have a wonderful night, everybody.